Last week we learned about the equilibrium constant, and we learned about it in terms of concentration. And so we saw expressions like this. The equilibrium constant for this chemical equation would be the molarity of SO2 squared, because it has a coefficient of 2, times the molarity of the oxygen squared, with the products on the top and the reactants on the bottom, SO3 molarity squared because of this. Well, in a gas reaction, the partial pressure of a gas is proportional to its concentration. So if we look at the ideal gas law, which, compared to all those kinetics equations, this should look like an old friend, right? PV equals nRT. So if we rearrange this, the units of molarity, moles per liter, right? Well, here's moles and here's volume in liters. So if we rearrange, we get P over RT is equal to N over V, and that is equal to the molarity of a gas. We usually don't talk about gas amounts in terms of molarity, but there it is. It's the partial pressure divided by the ideal gas constant times the temperature. So as long as the temperature is staying the same throughout the reaction, the molarity is directly proportional to the partial pressure of the gas. So we can express the equilibrium constant in terms of pressures instead of concentrations, because for gases often it makes more sense to measure their partial pressures. So for that same equation, in partial pressures, the equilibrium constant would be the partial pressure of SO2 squared times the partial pressure of O2 divided by the partial pressure of SO3 squared. So it's taking the same form as for concentrations, we're just using pressure instead. Any questions about that? So the value of the equilibrium constant in terms of concentration is not necessarily the same number as the value of the equilibrium constant in terms of pressure, but there is a relationship between them. So the partial pressure of a gas in atmospheres is not the same as the concentration of molarity. So let's look at that relationship. I already did this, but I'll do it again. So we have the ideal gas law. And if we divide both sides by V, those V's cancel out. And then we divide both sides by RT. And the R's and the T's cancel out. Wait a minute. You see what I did wrong there? This V doesn't cancel out. I got carried away. So N over V is equal to P over RT. So the molarity is related to the partial pressure. The molarity is the partial pressure divided by the gas constant times the temperature. So we could say that the concentration of A, which is N over V, is equal to the partial pressure of A divided by RT. So we could write the equilibrium constant in terms of concentration from this generic equation. So what would that be? We're going to look at the products. Talking about concentration. So we need the molarity of C, with the molarity of C. And does that have an exponent? Yeah, the little c. And then we multiply that by the molarity of the other product. And the exponent is its coefficient. Is it coming back to you at all? I think you guys stayed up too late studying last night. And then we're going to divide by the reactants. The concentration of A to the A power and B to the B power. Well, if A, the concentration of A is equal to the partial pressure of A divided by RT, we could put this in for the concentration of A. And if this is true, then the concentration of C is the partial pressure of C over RT. Right? So, instead of the concentration of C, I've got the partial pressure of C over RT to the C power, the partial pressure of D over RT to the D power, divided by the partial pressure of A over RT to the A power times the partial pressure of B over RT to the B power. I don't expect you to be able to reproduce this derivation, but I expect you to be able to follow along and say, oh, I see how that works. Okay, any questions yet? So we've kind of got a mess here, right? Well, there's RTs all over the place, right? So we could factor those guys out. So we could have PC to the C power and PD to the D power divided by PA to the A power times PB to the B power. And then this is going to be times, we've got 1 over RT to the C, 1 over RT to the D, 1 over RT to the A, and 1 over RT to the B. Well, that made things look worse, right? But we can simplify. If we multiply something, here's, well, let's do it this way. If I have x to the y times x to the z, that is equal to x to the y plus z. That's what the math people tell me. So I can simplify this then and say, well, this is 1 over RT to C plus D, 1 over RT, A plus B. Well, not quite, because I can't leave this part out. So let's fix that. There's just not enough room here. That's not great. Yeah, that's better. Pull those guys back down. I want you to. There we go. Phew. Save that one. When we invert something, what does that do to the exponent? If we want x, and we want to make it 1 over x, we raise it to the negative 1, right? So if I make this exponent negative, then I can say this is RT. Again, there's just not enough room here. So this part is the same as RT to the negative C plus D. And down here, this part is equal to RT to the negative A plus B. I've got this guy divided by that guy. So when I divide things, I subtract the exponents. So that's going to be RT. And we've got negative C plus D minus, minus negative A plus B. Isn't that a lovely mess? Which we could also write as A plus B minus C plus D. So, sticking those things together, KC is equal to PC to the C, PD to the D, over PA to the A, and PB to the B, times RT A plus B minus C plus D. Clear as mud, right? This part right here is called KP. So I think on the next slide here, there is a leap in total let's do this. So that's where we were. So this is equal to KP times RT to the A plus B minus C plus D. Well, if we want to define this in terms of KP is equal to what, we're going to divide both sides by this guy. So KP is KC divided by RT to the mess. If we bring that into the numerator, we're going to change the sign again. And now we're going to have C plus D minus A plus B. This part right here is equal to delta N. So that is the number of moles of gas, products, and gas reactants So delta, final minus initial, C and D are the final or product moles of gas, and A and B are the reactant moles of gas. So the difference in the number of moles of gas. So if we have the same moles of gas before and after, then Kp is equal to Kc. But if it's different, then it's not. Questions? Well, let's use that guide. So, and this is an equation I'm not going to require you to memorize. I'm giving it to you. Kp is equal to Kc RT to the delta n. Yeah, you got to put the parentheses on there. Because it's not just T to the delta n, it's RT to the delta n. So here we're given a chemical equation and the value of the equilibrium constant in terms of concentration. And we're asked, what is the value of Kp at that temperature? So Kp is going to equal Kc, which is this guy right here, 6.2 times 10 to the second, times R. What R do you think we're going to use here? 8.314 or 0.08206? We're talking about pressures, which are measured in atmospheres, right? We've been using, I'll just write them both down here. So the ideal gas constant can be expressed in different units. This is the value we use when we're doing ideal gas calculations or gas law calculations. And these are the units that have to be used with it. Here's atmosphere, unit of pressure. You can express that in different units. You get a slightly different number, 8.314 joules per mole Kelvin. And that's because liter atmospheres is a unit of energy or work. So because we're dealing with pressures here, we want to use this value. So we're going to have 0.08206 times the temperature in kelvins, right? So 298, and that's going to be raised to the power of delta n. So delta n is the number of moles of gas products. How many moles of gas products do we have? 2. And we're going to subtract the moles of gas reactants. So we have 1 plus 1, right? So that adds up to 0. The moles of gas isn't changing, and so this exponent is 0. And therefore, for this equation, Kp equals Kc. Any questions? Okay, so no questions? Oh, good, I got the right answer. Okay, so when I was doing this, I was leaving the units out here. I kind of did that on purpose because I knew they weren't going to work out very well. So what's up with that? Well, let's see what's up with that. So formally, meaning like officially, the values of concentration or partial pressures in those equilibrium expressions are ratios of the concentration or pressure to a reference. The reference is exactly 1 molar or exactly 1 atmosphere. So if we've got, we're talking about, the concentration of A, well, that's going to be, let's say, 0.25 moles per liter divided by 1 mole per liter. And so the units cancel out, and thus the equilibrium constant has no units. Okay? Because they've canceled out in the concentrations and the pressures. If we're looking at, the partial pressure of A, maybe it's 0.5 atmospheres. Well, it's 0.5 atmospheres divided by a reference, and the reference is 1, and so the units cancel out. You could say, well, this is just a trick to get rid of the units. Well, maybe it is, maybe it isn't, but it's what they do. So 3.7 molar is 3.7 moles per liter divided by 1 moles per liter. And so that's just 3.7. So, provided we express concentration and molarity and partial pressure in atmospheres, we can simply drop the units. Instead of writing this divided by 1 in the unit and all of that mess, we're just going to understand that that happens, and we're going to drop the units. I'm not going to test you on this idea, but some of you are with me in caring a great deal about units, and I don't want you to be disturbed by what happened to the units here. This is what happened to the units, okay? If you don't care about units, then you probably don't care, and you're just thankful that the units went away for a little while, and you're good, right? Any questions? Okay, so here's a question. Under which circumstances are Kp and Kc equal for our generic equation here? If A plus B equals C plus D, if the reaction is reversible, or if the equilibrium constant is small. Well, this is what we talked about. The total number of moles of gas is the same before and after the reaction. Got lost in my slides. So does that say anything about being reversible or having a small equilibrium constant? No. If A plus B equals C plus D, well, what is that saying? That is saying this is the moles of this gaseous product and the moles of that gaseous product. Total moles that you start with. And C plus D, these are also gaseous products, total moles that you end up with. If you have the same number of moles on both sides, when you do that complicated derivation thing, all the RTs cancel out. It's so awesome. If it's different, they do not cancel out, and then we have to keep them in there. So the answer here is if A plus B equals C plus D. So total moles of reactants in the gas form, total moles of products in the gas form. Any questions?